today. I am Tanvi Chanderiwal and I am pursuing my intelligence machine learning from Cambridge University in India. It is a pleasure and an honor for me for today's IEEE podcast. I am really excited to be a part of this wonderful platform where we get to learn, connect, and explore the latest trends in technology. I hope we all find insightful and experience today. Without further delay, we begin this exciting journey of learning and discovery. For those who are joining us today, IEEE PathX is a platform designed to provide students and teachers with opportunities to interact with professionals, researchers, and experts from different technological domains. It aims to bridge the gap between academic learning and real-world technological advancement, giving us valuable exposure to new ideas, research, and career possibilities. Today, we are going to explore a very exciting and rapidly emerging field, quantum computing and its integration with artificial intelligence. We are living in a time when artificial intelligence is transforming almost every industry. While quantum computing has the potential to solve certain complex problems in fundamentally new ways. The combination of these two fields, often referred to as quantum machine learning, open us exciting possibilities for developing more advanced and efficient learning models. Understanding these emerging technologies is important for students because they are not just shaping the future of computing but also creating new opportunities in research, innovation, industry, and technology development. And to help us understanding this fascinating field, we have an expert with us today. It is my privilege to introduce our esteemed speaker, Mr. Sachin Namdev. Mr. Namdev is currently working as a project engineer in quantum computing group at CDAC Bangalore. He holds an MTech in computer science and engineering with a specialization in artificial intelligence from the Defense Institute of Advanced Technology, Pune. During his MTech, his research focused on quantum long short-term memory or quantum LSTM networks. At CDAC, he is actively involved in research on quantum convolutional neural networks, quantum CNNS, and hybrid classical quantum machine learning. His work focused on exploring the integration of quantum computing with modern AI architectures and developing quantum enhanced learning models. His expertise lies at the interaction of artificial intelligence, machine learning, and quantum computing, making his experience and insights extremely valuable for everyone interested in emerging technologies. So, without taking much of your time, let us warmly welcome Mr. Sachin Namdev, sir. We are honored to have you with us today. We look forward to learning from your knowledge and experience. Over to you, sir.
Yeah. Hi, are you able to see me right?
Yes, sir.
Okay, wait, let me just present my screen. Okay, so this session would be divided into two different things. First, I would introduce you to what exactly is quantum computing, and then we would jump to what exactly is quantum machine learning or how you can do quantum machine learning. So, first and foremost, like what exactly is the quantum computing, we would see the non-mathematical way of doing things. Okay, I'm not going to go into too details about the mathematics, but I'll tell you how the things happen. So before we jump into quantum computing, we need to know why do we need quantum computing. So as you know, some problems becomes extremely difficult as their size increases. Your classical systems, your classical what can you say, HPC systems can't basically simulate very complex systems. Like simulating very complex molecules like a long chain polymer molecules, or even quantum systems itself. 20 to 30 qubits is what a normal HPC system with 1 terabyte of RAM can basically uh, do. If we go more than 90 qubits, okay, what exactly is qubit we will see, but nine you know the factor that 90 qubits is not simulatable even if you combine the computational power of all the computers in this world. Okay, even all the computers, all the resources, even if you combine them, it is not simulable more than 90 qubits. You cannot simulate more than 90 qubits. But the complex problems require more than 90 qubits. Your basic simple, like your, there is one algorithm called Shor's algorithm, which is basically used to break the RSA cryptography. Now that basically requires more than millions of qubits and even millions of gate operators, optimizing complex systems and solving certain cryptographic problems. Like I said, RSA, breaking the RSA cryptographic form of qubit is nothing but the full form of qubit is nothing but quantum bit. Is nothing but the basic unit of information in quantum computers. You may have seen this type, and these are eigenvalues. So you need to know a little bit about linear algebra, then you would be able to understand this. But since I'm not going too deep into that, so basically you have to understand beta is nothing but the probability of getting that particular state, alpha betas, and 0 and 1 are that particular states. Then only you would get that, yes, my state is equal superposition state. Now, as I had told you, that we need quantum gates to basically do operations on quantum states, okay, on quantum computers. Then we get the correct answers, or we reach the, or we do the operations. So basically quantum gates transform the quantum states. You have this particular state and I want to change this state, I would have to apply one of these gates depending on what I want to do. So these are not the only quantum gates. There are much more quantum gates there, but I'm restricting myself to basically help you understand. There are something known as poly gates. There is poly X, poly Y, poly Z, and identity gate. So poly X gate basically does a bit flip operation, just like we have a classical or quantum mechanics. There is one special system where we have phases involved. You are seeing this, right? This plus state. This means that there is a positive state or positive 180-degree movement. If this was negative, it was in the opposite direction, negative state. So poly Z gate helps you to change that. Now, why do we need to mess with the phases? Is because these phases create interference, and these interference helps us to get to the correct answers much more faster than classical systems. Now, there is one special gate, Hadamard gate. This basically creates or removes certain superposition. Certain superposition means basically meaning equal superposition. Or if you have any other way of superposition also, it helps to remove that. But basically it is used to create equal superpositions. Now, one of the basic thing of any quantum gate is, if you apply the quantum gates, we call them unitaries. Okay, unitary basically meaning they represent a matrix, a unitary. And if we apply the complex conjugate transpose, basically the inverse or the opposite of it, we get the identity state back. So basically, if I apply Hadamard gate, I would get the equal superposition. And if I reapply a Hadamard gate, I would get the identity state or the state which I started. So Hadamard gate is itself a complex conjugate transpose of itself. And you have poly X gate as well. So if you apply the complex conjugate transpose of poly X gate, you would get the bit flip, before the bit flip, whatever the state is, back. So your quantum gates are unitary in nature. If you apply U, and if you apply the complex conjugate, you get the exact state whichever you started was back. Like let's say we started with get 0 or the 0 state, and we apply one of the gate operations U, and we apply the complex conjugate transports, we get the state 0 back. So these rotation gates are much more useful in quantum machine learning. So these rotation gates also help you to transform your quantum states and basically do the quantum operations. Like let's say your Hadamard gate. So each of your gate has a specific matrix. This is the matrix which is used to basically uh, work on the quantum states. Your quantum states, since it is a linear combination of linear algebra, you basically have vectors and matrices. So basically, all these gates are also matrices. The representation is matrices. Action on computational basis. Computational basis is basically 0, 1 or the exact states like 0, 0, 0, 1, 1, 0, 1, 1, not the uh, other states. Okay, so basically these states, if I apply Hadamard gate on 0, I would get plus state. If I apply Hadamard gate on 1, I get minus state. So applying gate to different bits also changes how you basically would get the exact state or exact quantum state for further processing. Now the simplest way to say even quantum's version of hello world is creating a superposition. Now as you know, simplest way to do it is apply a Hadamard gate. So what you do, start with one qubit and initialize it to 0. Okay, 0 initialization, prepare superposition via Hadamard gate. I would apply Hadamard gate to it and get the plus state, and this shows that my gate, I am creating a quantum hello world operation. And you have to do measurement as well. After many shots, you would get approximately 50% of 0 or 1. So this is quantum's version of classical version of hello gate in the quantum way. So the quantum version of hello gate, hello world. So what this basically teaches us is, this shows that quantum program can prepare a state whose measurement is probabilistic. All the quantum states are probabilistic in nature. Okay, once you measure it, you get the probabilities. And critical interpretation is, this does not mean the computer simply randomly chose 0 or 1. It's not randomly choosing 0 or 1. Because of this amplitudes which were there, we were getting those states back because of those amplitudes only. So before measurement, the qubits representation is by a superposition. But after measurement, we only observe the classical value. Your quantum systems are not randomly putting out the bits or randomly choosing the bits. Whatever the quantum state was before measurement is helping you to get those, but their phases are different. Both will give, when you measure these two, both will give 50-50 probabilities, okay, in the ideal cases. But since both of them have different phases which can affect later quantum operations. Now if I apply some quantum operations after this, they would be in two different states. Okay, their states would be completely different. They won't reach the same state. Right now here they are at the same state, but their phases are different. These phases help us to basically get to good states or our answers via quantum interference. So as you know, interference, basically we have two types of interference. Constructive interference, where amplitudes basically reinforce one another. If you see these points, okay, or basically if you have seen Young's double slit experiment, right? Young's double slit experiment, what it did was, after the experiment, you got like white, black, basically, what can I say, stripes, okay, and the middle stripe was basically the most brightest as compared to other. That was basically because your photons interfere with each other, okay, it interfered with itself, and it was in equal proportion of everything, just like this particular thing. So let's say these are the holes or the slits where the photon had to go. Now after uh, basically you, if you did not observe it, your photons would be in basically interference with each other. Because of that interference you get that particular pattern. If you basically do the double slit experiment and you basically see which which slit the photon goes, you won't see that interference pattern, that white black. You would only see two different, basically two basic thing, and with the constructive like your Z gate. In that case, if you look here, I start at 0, I apply Hadamard gate, I reach a plus state, then I apply a Z gate. Now what Z gate does is, it basically only does the phase change if your state is 1. So whatever the probability of getting this state was, this P plus would basically change to minus, and this minus was basically changed to plus once you apply Z gate. Now if you see here, plus changed to minus because that phase changed, and then you apply Hadamard gate again and you get 1. So basically with interference you basically changed your quantum state. You started somewhere else, you reach somewhere else. So this is why quantum algorithms use interference to strengthen useful outcomes and suppress unwanted outcomes. This is mostly used in all of the basic algorithms like your Grover search, Shor's algorithms, as well as DJ algorithm, BV algorithms, Burstyn-Vazirani algorithm, or Deutsch-Chooser algorithm. So basically, do those quantum algorithms in one go or much more faster. Now you have something known as multi-qubit system as well, where basically two qubit system has four basis states. Why? 2 to the power 2 basically means four different combinations, and we call them basis states. So if it was 3 qubit, you would have 2 to the power 8 equal to 8 basis states. So 2 qubit system, let's see for that, has four basis states. Four basis states where your quantum states, or after measuring, you would get these bit strings only. You won't get any other bits. So general 2 qubit system is written like this, where each of the states has some amplitude associated with it, which gives the probability of getting that. So for n qubits, you would have this general formula. Whatever the state is, whatever these states is, it would have some amplitude associated with it. And a general n qubit state contains 2 to the power n complex amplitudes, because we represent 2 to the power different n states, and each of the 2 to the power n state has to have some probability of getting that. So you would have 2 to the power n complex amplitudes, which would basically tell you the probability of getting those states. Now one more thing. Now, basic difference between superposition and entanglement is, superposition only happens with single qubit. It only happens with itself, only one qubit. And for entanglement, you need multiple qubits. So entanglement is linking two or more qubits so that one qubit state instantly dictates another qubit's state. You may have heard about basically taking one of the particle, and let's say two particles are there. Okay, let's say these two, they are entangled with each other, and if I take them apart, okay, light years apart, if I measure one, I instantly know what is the second qubit's state. Okay, so that is what entanglement is. This is also what baffled Einstein. Okay, like even after separating them out light years ahead, the information that was basically sent when measuring this, and when measuring one of the particles, I instantly knew what the other particle was, even though they were light years apart. That communication was much more faster. That is why it also baffled Einstein as well. But what exactly is entanglement is, mathematically, an entangled state is a multi-qubit state that cannot be factored into individual states or separate qubits. If you look here, I know what those states are. I can separate them out. But if I'm not able to write my state in this way, okay, the combination in this way, my states are entangled. My qubits are entangled. So what entanglement means, the qubits cannot be described independently. Okay, they are dependent on each other. The complete multi-qubit state must be considered, then only we would be able to basically say that entanglement has happened. And measurement results would be strongly correlated. That means measuring one would instantly tell me what is the state of the second. But entanglement does not enable faster than light communication. There is no actual communication happening. But we do not know how basically that communication actually is happening between those two states, but it is not enabling those faster than light communication. Multiple different theories are there, but we won't delve into that. The most famous example is Bell state. For entanglement, there are four different Bell states, which was given by John S. Bell in 1964. Now, what exactly is a Bell state? There are four ways of Bell state, but we'll look at one of the Bell state. First Bell state, we call it Chi plus. Chi plus basically represents this state. Chi minus is basically minus state. Now there is two more states, phi plus and phi minus, which basically means 0, 1 and 1, 0. Instead of 0, 0 and 1, 1, we have 0, 1 and 1, 0. And again plus or minus. So four different Bell states. So how do you create a Bell state? Start with two qubits in state 0, apply Hadamard, so you get equal superposition because you apply Hadamard to the first qubit. This basically, sorry, this qubit. So this is in equal superposition. Now you apply a C0 gate. A C0 gate is a 2-qubit gate. After applying C0 gate, basically, which only applies if this or the target qubit is basically 1, then it flips the state of the other qubit. We would see this. I know this is a little bit complex to basically get into this, but we'll see this in our own platform called Quniverse, where it would be much more easier for you to understand. But for now, understand that applying C0 gate, you would get this state. This results in approximately getting 50% of 0, 0 or 1, 1. You won't get 0, 1 or 1, 0, but you would always get 0, 0 or 1, 1. This state is called as a Bell state. Okay, this is repeating. Now we come to what exactly is quantum algorithms. Now in a quantum algorithm, you do a sequence of quantum gates to design and solve the problems. General workflow is you prepare the qubits, you encode your problem. Now encoding, we will see how you do. Apply the quantum operations, use interference if you want to use, measure the output and post-process it classically. Now types of algorithms are searching algorithm. One of the good searching algorithm is Grover's algorithm. It is much more helpful in unsorted data. In unsorted data, your time complexity is O of n. But for Grover search, it is root O of root n. It is quadratically, there is a speed up as compared to classical part. Now Fourier and period finding algorithms. Yes, sure. Quantum Fourier transform, quantum phase estimation. These help you, these two help you to find out the periodicity, which help you to decode or which is used in Shor's algorithm. Simulation algorithm, like for example, for quantum chemistry, you use VQE, variational quantum eigensolvers. For optimization, you also have QAOA. Now, QAOA and VQE are hybrid. These represent your actual QML algorithms, your QML algorithms from the quantum perspective. There are QML algorithms which from classical perspective, your quantum CNN, quantum LSTM, where okay, and quantum machine learning algorithms like quantum kernels for SVM and variational classifiers. Okay, basically your quantum circuits doing your or quantum neural networks doing the classification. Now, this algorithm was one of the first algorithm which basically told us or told the world that yes, quantum supremacy or quantum advantage is possible. The problem is this Deutsche given a function determine whether it is constant or balanced. That means it does not matter if you have f of x, it does not matter what x I give. For constant, I would get the same output. For balanced, I would get two different outputs, but 50-50% of time. So half of the outputs are 0, half are 1. So classically, to do this, I would need to do n by 2 plus 1 operations. Okay, n by 2 plus 1, I would have to basically give the inputs. Okay, if I have 1000 inputs, I need to give 501 inputs. Then only I would be able to determine if it is constant or balanced. But the quantum version, you would only have to use it once. You would only have to run the circuit once, basically one time for the number of shots, and you would get whether it is constant or balanced in one go instead of running it 501 different times. So classical approaches require many function checks. You have to basically run it many times. But quantum approach can solve it with one query, the ideal case. So if I run it, I basically do this measurement. This is the circuit for balance function. You prepare the state, you do these operations, and you do the measurement. If I get probable 0 0, okay, 0 0 0 in all the qubits, okay, 0 here, 0 here, 0 here, 0 here, my function is constant. But even if I get 1 anywhere, okay, 0 1 0 0, that means my state or my function is balanced. This is what showed the world that yes, quantum advantage is possible. Instead of doing n by 2 plus 1 checks, I can do it in one go. Then you had Grover's algorithm, where you have to search in unsorted space. Instead of O n, you have O of root n. You basically apply an oracle, which basically marks your state, then diffuser. So basically applying and diffusing this for root n times, you would get your state back, your what you wanted to search back. So if there are 1 million possibilities, classically you would have to search 1 million times, because our worst case scenario is O of n for unsorted. But Grovers only need to do 1000 checks, which is quadratically speed up. Then you also have Shor's algorithm, one basic algorithm for determining or breaking the prime numbers, to determine the prime numbers. So to find out the prime factors of large numbers, we use Shor's algorithm. Now if you look here, this is the quantum circuit to factor 15. Your quantum gate operations on Shor's algorithm basically increase by O of n cube, where n is the bit size. Okay, if my basically integer has n bits, I would require n cube number of operations to basically find out the factor. Now basic difference between Shor's is one one of the thing is Shor's does not directly give you the what is the answer, what is the basically the factor. It only gives you the periodicity. From that periodicity, you find out the answer. So Shorts is not giving you directly the factors. Shorts is helping you to speed up that process of getting those factors. Now, why Shor's is important? Large integer factorization, and Shor's algorithm gives exponential speed up compared to best known classical methods. Now, how Shor's work? Convert factor into period finding, use quantum superposition, apply model exponent. You have to use quantum Fourier transform, estimate the period, and use classical maths to recover your basically the factors. Now we come to hybrid quantum classical computing, your actual QML algorithms. Most of the near-term quantum workflows combine classical and quantum computation. Your typical loop is classical computer selects the parameters. Since quantum computers right now are not much more powerful that we can run everything in quantum computers, we use some part quantum, some part classical. Like basically running the problem in quantum part and optimizing via classical parts. The quantum circuit prepares the state, measurement estimates the objective, and classical optimizer updates your parameters. That is how hybrid or any QML application works. Your QML application is known as a parameterized quantum circuit. Why? Because it requires, just like your classical neural networks or classical ML algorithms, we have weights and biases. Here we have the parameters or the angles of rotation gates. Rotation gates are parameterized gates, which help you to do the quantum ML just like your classical ML. Your examples are variation quantum eigensolver, VQE, quantum approximate optimization algorithm, QAOA, and variational quantum classifiers or your QNN. Now, before we jump to the QML aspects, we need to know how a real world problem reaches your quantum computer. You actually start with the real world problem. You have the cost function of the real world problem. Basically, write the cost function of the real world problem classically. Okay, just like classical maths is there, you would write that. Okay, to find out the best delivery route, to find out the molecular ground state energy, scheduling, or identify a high quality solution from n possibilities, you would have the classical cost function. Now that classical cost function has to be converted to a QBO, quadratic unconstrained binary optimization, a HUBO, higher order binary optimization. Basically, since quantum computers right now can only do binary optimization, so you'd have to convert your problem, okay, to a binary optimization problem or direct Hamiltonians in basically molecular chemistry. But basically, you'd have to convert them into one of these two things depending on what you're trying to solve. And from this, for the cubo part, you basically convert it to Ising part, then Ising to Hamiltonian, and that Hamiltonian is basically what your quantum computer is using to solve the problem. You can think of Hamiltonian as the quantum's way of cost function. Just like you in your classical machine learning, you have some cost function, you try to minimize that, okay, or you try to maximize that. In basically quantum mechanics, we have Hamiltonians. That is exactly what you can say is the cost function of your problem, which you have to try to minimize. Hamiltonian, you would have to try to minimize. So whatever your classical cost function is, if it is in maximization, you would have to convert it to minimization and then convert it to Hamiltonian. And that Hamiltonian is what your quantum computer uses to find out the gate operations, what type of gate operations it needs to do, and then you would get the optimized version. Now you have multiple ways of computing this Hamiltonian as well. You can use annealing based on quantum annealers, where you do not have to do gate operations. It basically evolves from something known as a ground state to your final optimized state. Or you can use gate operations, discrete gate operations, like you have seen those Hadamard gates and everything, using quantum approximate optimization algorithm. So there are two different ways of quantum computing as well. Annealing based, where you do not have to apply a gate, and discrete gate based, where you are applying discrete gate operations. Now let's switch to quantum ML. Now I have told you that we have to basically convert our problem to your quantum problem. But before that, we have to encode our data as well. You would have to convert your classical data to quantum data. Now, how do you do that? You do via encoding. Why? Because your quantum hardware only understands amplitudes, entanglements, and superposition. It does not understand what is number, what is table, what is image or text. It only understands amplitudes, entanglements, and superposition. So you need a good encoding choice for which would give you compact circuits, higher accuracy, and faster results. So what are the encoding principles? First and foremost is amplitude encoding. We know we have amplitudes in quantum states. So we convert our classical data into amplitudes of those quantum states. So you can think of this as compression master. It basically packs an entire data vector into amplitudes of a multi-qubit state. You can think of it like zipping 1 GB file into 1 MB archive. So let's say you have your data vector where you have number of features, right? If let's say iris data is there, you have sepal length, sepal width, petal length, and petal width. Now that particular sample would have value, and that sample we consider as one vector composed of four features. Okay. Now we have to, those four features would be in numerical. You would have to normalize that feature vector so that the squared entries, okay, four features are there, so the sum of the squares of those four features should sum to 1. And once that happens, you basically you prepare it via this way, where xi is each data component after normalization and I is the state. Okay, if xi is zero point 0.8 and I is 0, 0, so your state psi would be 0.8, 0, 0, and then other of those combinations. So the pros is it is logarithmic qubit scaling. Your 1000 features get compressed to 10 qubits because one qubit requires 2 to the power n qubit required 2 to the power n states. So 2 to the power n features can be represented with n qubits. But it requires complex state preparation and precise normalization, which is very difficult to do if you are a beginner. Second thing is angle encoding. This is one of the most simplest way to encode your problem, encode your feature vector into quantum state. The same thing you would do, you would have to normalize that, but you do not have to ensure that squared entry is sum to 1. So basically, again, we take the iris data, you would have four features. Now you do the normalization between 0 to 1, but you do not have to ensure that this particular thing happens. You do not have to ensure in angle encoding. Okay, you would have to, for each feature A, you scale it, basically normalize it with some scale. Like if I am doing min max normalization, okay, so whatever xi is there, I would must subtract minimum and divide by maximum minus minimum. And that particular normalized value acts as the theta or the angle for your rotation gate. So hence, once you apply, let's say I am going to apply Rx gate. Okay, I have four feature vector. I need one qubit for each feature vector, and for each feature vector after normalization, I would apply Rx gate. Let's say, and Rx x1, Rx x2, Rx x3, Rx x4 on each different qubit. After that operation, I would get my quantum state, which represents my classical data or classical sample. And I can also use multiple rotations for richer feature mapping. Pros is it is very simple circuits are there. You only need simple rotation gates, and if you are a newcomer to quantum machine learning, it is very much intuitive. But cons is it is linear qubit scaling, and you have to map each feature to its own qubit. So you have n features, you need n qubits. So if you have 30 features, you need 30 qubits. And then there is also basis encoding, which basically maps each classical bit to a qubit. So if you have your data, you convert it into binary form, and that binary form is basically how many number of qubits you need. So if, for example, if binary form, if my decimal form, I convert it into binary form, looks like this. I need 5 qubits, and if one is there, that means I need to apply an X gate for that particular qubit. So it is trivial to implement and minimal circuit depth is there. There is no compression and needs as many qubits as bits, which is very much impractical for large data sets. Are you following me till now? If you have any doubts or anything, do you want to ask? Do you have any doubts or anything?
No, sir, no.
Okay, okay.
I am having some queries. We'll ask at the end.
Okay, okay, no issues. So basically, if you look at amplitude encoding, we use it in the quantum's version of principal component analysis. Your angle encoding is used in any other QML algorithm or variation quantum classifier, your quantum neural networks. And basis encoding is basically used in Grover search. So you do not use basis encoding in QML applications. How do you choose what encoding principle to do? If your data size and dimensionality, okay, depending on that, if n is very greater than the qubit widget, n here represents the number of features, is extremely greater than the qubit widget. For example, let's say you have millions of features and you do not have that many number of qubits that can represent those million number of features. You can use amplitude encoding, so which would be basically able to compress that much data into very few qubits. If n is small, let's say you have 30 to 40 or 30 35 features, and you value simplicity, and 30 to 35 features is still doable in modern high HPC, high powered computing devices, so you can use angular basis encoding. Now hardware constraint also happens. Now since these circuits have to run on actual quantum hardwares, and actual quantum hardwares are very much noisy and cannot run too much quantum gate operations for too long, so you would need to know according to what hardware you are going to design your circuit or encoding principle. If your hardware can run deep circuits, but today's hardware, deeper circuits means more error on noisy devices. Noisy devices is current quantum computers. Shallow circuits or very compact circuits are much better for today's machines. So you need to use angle encoding in that case. And development of it, amplitude encoding for each sample requires much more engineering time, whereas angle encoding is much more quick to prototype. Now there are also something known as feature maps. So basically your encoding is like placing a camera there, but not focusing on the details. Feature maps help you to focus on the details. So formal definition is, a feature map is nothing but a parameterized quantum circuit. It has parameters that embeds classical data into quantum state. Your key purpose is to project high data into high dimensional quantum space, to amplify certain non-linear patterns, and to serve as the kernel for quantum algorithms, quantum SVM, quantum K, K means as well. So these feature maps also are the ways that why we have quantum versions of classical SVM or your classical ML algorithms. For example, for support vector machine, classical support vector machine, I require a kernel which would map it to higher dimension. So if I use a quantum circuit for that kernel, it becomes a quantum SVM. So circuit mechanics, basically how you create the feature maps is you have to do parameter assignments. We basically would want angle encoding, which is basically it is much more simple. Single qubit layers of rotation gates on each qubit, and tangling layers C0 CZ gate between each qubit, and repeat that depth, and then do the measurement, which would give you the answers or basically for further processing. Now two types of feature maps are there. One is poly feature maps, which basically means we have poly gates X, Y, Z, rotate qubit by a data driven angle about X, Y, Z, and optionally entangle. So basically you have some rotation gates RZ, RY, RX, RY, RZ. This is a decomposed version, but RX, RY, RZ you use to basically do or create poly feature maps, and then you can use C0 and CZ gates. There is also ZZ feature map, where instead of RX, RY, and RZ, you only use RZ and apply a control phase gate between the qubit pairs. So this is also again a decomposed version, but basically using only Z or RZ gates, with only RZ gates and RZZ gates. Ising ZZ gate. There is also an Ising ZZ gate, which is basically decomposed into this. So this P here is nothing but your RZ gate. So H, RZ, 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 C naught, RZ, C naught represents RZZ, which is a little bit complex thing, but it is much more useful when you are doing gate based optimization from Hubo or Ising. So basic encoding, your amplitude angle versus feature map is your basic encodings only load your data, but quantum feature maps transform and enrich your data. Your patterns captured is only linear in basic encoding, but you can capture complex and multi-feature relationship in quantum feature maps. Your basic encoding is much more useful in quick demos, but if you want to do research on actual research on quantum machine learning, you need to use quantum feature maps. Now, trainable parameters quantum circuits, these are nothing but your actual quantum circuits with parameters like your RZ gates, which basically, let me show you. Yeah, if you look at here, this is a typical parameterized quantum circuit which can be used for quantum machine learning applications. Okay, so for quantum machine learning application, your circuit basically has some input layer where you are encoding your data. Sorry, these are the vertices, and this
Vertices,
is
and these are the edges, right?
wherever edges are there, there is only the possibility of connecting those two qubits.
Okay.
So if you see here, there is no edge between there.
Yes, so there is no connectivity.
So there is no connectivity between these two. So I
Mm.
cannot, in my designing of the quantum,
Directly it cannot go, but via it can.
via also you cannot go.
Kyo? Well, the next node is connected with this, and then we are
No,
going
no, no,
down, and
no.
then
I wanted to connect this qubit with this qubit, but I'm
right.
connecting these. This does not
Yes.
mean this qubit is connected to this qubit.
Okay.
Connection means this qubit is going to affect this qubit. But here it what means this qubit is going to affect this qubit. And this
Mm-hmm.
qubit is going to affect this qubit. This qubit is going to affect this
As
qubit.
there is a connection to the next node, only those qubits
No, no.
can affect each other.
Yes. So
Okay.
since there is no connection with this qubit cannot
Uh-huh.
affect this.
And
I
if we
cannot.
go to the near below diagram, where there
This.
are only the nodes, है ना? I think yes,
Yeah.
vertices. Okay,
But
okay, I got
edges
it.
are also there, but
Edges are also there. Yes, 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 yes,
the
yes.
thing is, this diagram is much more. It is this only. You would
Uh-huh.
see, I think, some small line is here, right?
Yes, 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 yes.
They are
I
connected.
got it.
They are connected.
Okay. So, from one node to the last node, matlab if we are taking this diagram as a single one, so from the starting there is no starting one, na? We have to go by this only.
No, no, no. When designing it, you have a starting. When you are designing, this is nothing
Mm-hmm.
but a quantum chip.
Quantum chip. Okay.
Okay, this is the structure of a quantum chip.
Okay.
And this is the structure why how which your quantum qubits are uh, basically placed on that quantum chip.
Okay.
If you have seen this kind of thing, I would show you quantum computer basically. You have seen this kind of things, right?
Yes, yes, I can.
This is a quantum computer, but
Mm-hmm.
this is not where qubits are there. This is just to cool that qubits.
Cool that qubits. You're right.
Qubit is nothing but just
And
like you
how does
have.
it cool? The temperature required here is it minus sorry
It is
273?
actually in millionth of Kelvin, minus
Minus yes 273 around, na? 0
हाँ,
Kelvin or more than that,
near
right?
to 0 Kelvin. It is near to 0 Kelvin.
Yes.
Basically,
Yes.
10 to power minus 6 Kelvin.
If we are implementing qubits in our PCs or jo bhi quantum computers, how we will make it cool then? These bits, how they will become cool?
Okay, when you are doing it on actual classical systems, you are doing simulations. It is not
Achha.
actual quantum hardware.
Okay.
Here, these particular parts, you use liquid helium.
Yeah.
Okay, liquid helium 4 and helium 3 to basically
Yes.
cool the system down. So
Mm-hmm.
there are stages of cooling it. Now, currently, right now, it would be in 0 degree Celsius or 273 degree
Yes,
Kelvin.
273 degree. Okay.
Now,
It's like
with
0 degree Kelvin.
you need to reach 0 degree Kelvin, but you are in
Yes.
0 degree Celsius right now.
Huh.
So what
So
you'll do with 0 degree Celsius, I would use nitrogen, liquid nitrogen,
yeah, I know.
to reach 50 Kelvin.
Yes.
Okay, this is over a period of 30
Mm.
to 35 hours.
Mm-hmm.
Then second stage of cooling, you would use liquid helium
Yeah.
to go from 50 Kelvin to 4 Kelvin.
Mm-hmm.
And then again, with the combination of helium 3 and helium 4, you would reach 10 to power minus 6 Kelvin, the exact point at which quantum fluctuation or the actual quantum mechanics happens.
I
So if
agree with this. So, Sachin sir, is it possible for our students and even me? I want if we have something in CDAC related to this quantum computing.
yes, we have basically a platform called Quniverse. I also wanted to introduce this to you. Let me introduce this Quniverse platform, and also we are basically, I think by November or December, our
Mm-hmm.
own CDAC's own 108 qubit actual qubit system, actual quantum
Oh,
computer
great,
would
great.
be there, and via Quniverse you would also be able to access it. But
And that's
let's basically tell you what exactly Quniverse is, how we came up with that. So basically, if you see here, learning your quantum computing is much more multi-layered. Okay, you
mm-hmm.
need to know mathematics. You need
Mm,
to
yes, yes, it
understand,
is pure mathematics. Yeah, I know.
it is
And
pure
I
mathematics. And even if for simulators, okay, even if
mm,
for one particular simulator, okay, you need to understand what those syntaxes are. Okay, for let's say I'm trying to understand Qiskit. I need
mm-hmm.
to know what syntaxes go into Qiskit. There is Circ, Penny Lane, CUDA Q, to basically all these different fragmented simulation frameworks or even
Yeah,
quantum computing frameworks are there. So before even you solve a quantum problem, you have to know these all concepts, even your frameworks. Now,
I
what
agree
we
with this. I agree, fully agree with this. But I just want to say that the diagrams which you shown to us, right? The working of the quantum qubits and the transmissions from one node to another. And another point is, you said na it's a 0 degree Kelvin on the minus
yes
273 degree. So do we have something like this in our CDAC? You are from CDAC
yes
Pune, right?
CDAC Bangalore.
Okay, CDAC Bangalore.
Yeah,
Okay.
that is what I'm saying. It is currently being built, and by
Mm.
November, you would have that. You would be able to have it. Uh, Basically, we would have our own 108 qubit. We have purchased it via Rigetti. So
Mm-hmm.
it is
Mm-hmm.
Rigetti's quantum computer. Okay,
No, it's
108.
okay. It's okay. So I know liquid nitrogen. I know the helium. I have seen it.
So this is how, basically, this is how it would look like if you are going to visit the
Nah,
quantum
yeah,
computing.
yeah. Certainly, if you will give us offer, to we will certainly visit that place.
Sure,
I
sure,
would
sure.
like to visit with my students. These students are the IEEE members. Certainly, I would give them an exposure for this.
So basically, if you want to visit it, I would suggest you would write to us
Yeah,
at
it's
universe@cdac.in.
uh, coordinator of this event. Kindly note down this email ID, and will certainly give a mail to the sir, and visit in the month of January after your exams.
Yeah, yeah, please basically do it so that we also give you a correct deadline or correct date.
Yes,
And
actually, the students they will have their exams in the month of November, December, so they may get free by January. So, will January we will certainly, you know, I will write down a mail to you and will get the permission. Who is
sure,
the
sure.
coordinator of this event? Kindly note down the email of the sir. Okay.
Universe@cdac.in. Okay.
We'll certainly do that, sir. I'm Dr. Nitika, sir. I'm the IEEE student branch counselor and I'm director working as a training and placement in this Sage University Indore.
And good to know you, ma'am.
Yeah.
And I also that your students can understand quantum computing without going too much into details into mathematics. You can please also you can purchase our subscription plans as well. Okay, you all you have to do is mail. Again, everything else is here only. You have to mail here. You do not have to do whatever you want to do, all those visits. Do you want to purchase this? Okay, let me basically, if time persists, I think we are a little bit much more fast. Let me show it to you much more quickly what exactly it is. So basically, instead of doing the mathematical thing, or instead of doing writing your own code again and again, we have a basically UI based approach to designing it. If you look here, this is my code for OpenQuasm or Qiskit or Circ or CUDA-Q. Okay, now your students can basically come here, drag and drop, design what exactly the quantum circuit they want to run for their problem, and they would get that code. If you look here, every code, you do not have to even learn about them. Okay, and now you want to run it on different hardwares. Okay, these simulators are there. We have simulators even on GPU. Okay, or on QPU, actual quantum hardwares. Okay, QI hardware, super stack hardware, we basically give them. But you would need your own API keys, because currently right now it is much more expensive. But these all things, depending on the credits, your students can basically run these, and you can also basically use this platform to basically teach quantum computing to your students.
Definitely. Actually, they may have this project-based learning. They have some a subject like this with minor project and
Yes,
all.
yes,
So we can work on this with this quantum and simulation kind, and it will
yes,
be beneficial for students for their upcoming one when they will compete for the next world or in placement and
upcoming
interview
world,
cell.
upcoming
Yes,
world.
yes, yes. Then they may require all this. So this is
Yes,
actually a good platform, sir. Very nice. I will certainly. Uh, I will share my email ID as well as the mobile number with you on
no,
your
sure,
mail
sure.
ID.
And,
Then we
if you
will.
want, you can note down my email ID. My email ID is this:
Mhm.
Sachin Ramdev at cdac.in.
Okay, sure. I will give this. I will write down a mail to you.
Yes. So for all communication, you can basically type to me or kinivas at cdac.in. Even for your visit or even to purchase this, you can basically come here.
Okay, okay. Thank you. Thank you so much, sir.
Okay. Now, basically, since I have taken a little bit much more time, so if you have any doubts or anything, if you want to know more about anything, if you want to clarify anything, if you have.